In this video, we are going to look a little bit at continuity. We'll review some of the continuity definition that we talked about before, but our focus of this particular video is to apply, examine, and understand the intermediate value theorem. So let's jump right to the lesson portion. If you're in my class, you'll do the warm-up in class and go through the homework during class. But I want to look particularly right now at the intermediate value theorem. So, according to, give me a second here, I'm going to move this up. Give myself a little space here. According to the intermediate value theorem, well, first of all, let's take the word apart, intermediate. The word intermediate basically connotates in between. So we're talking about a value that is in between, and therefore we talk about the intermediate value theorem. So it has something to do with a value that's in between other values. Let's look at the condition of this particular theorem. Oops, my highlighting didn't move. Let's move that up. All right. So condition. This is a conditional statement, like from geometry, an if-then statement. If you have a function whose name is f, if you have a continuous function. So the first thing you see about the intermediate value is that the first condition is that you must have a continuous function. And we talked about continuity yesterday. The function's continuous on a closed interval. So it doesn't mean that the function is continuous everywhere, but it's continuous on a particular closed interval. So that would be condition number 2. We must have a closed interval. And so just to help you to understand that, let's say we had a graph that had a vertical asymptote, and it did something like this, and then maybe over here it had a point discontinuity. So clearly this function has a discontinuity at, we'll call this A, and we'll call this B. There are discontinuities at A and B. However, if we close the interval, let's say we chop it off here and we chop it off here, and we call this C and D, the function is continuous over the closed interval from C to D. So we could apply the intermediate value theorem on that interval, on that function. However, if we tried to apply the theorem from, let's say, over here we'll call this E. If we tried to apply the theorem from E to C, the theorem does not apply because the function is not continuous everywhere over that closed interval. So we got our first condition out of the way. All right, if f is a continuous function on a closed interval and k is any number between f of a, now keep in mind f of a is a y value, a is an x value, f of b is also a y value, and x is the value that generates that y value, b. So k is any number between f of a and f of b, or k is a y value, because what it says is that k is between f of a and f of b. F of a is a y value, f of b is a y value, so we're talking about any number between f of a and f of b. If the function is continuous, and k is a number between f of a and f of b, then there is at least one number c, again, c is an x value, inside of the interval such that f of c is equal to k. And this is my thing, I personally call this a duh theorem. Now in words it sounds very, very confusing, and it sounds very fancy, but it's really quite simple. Basically, what the theorem is saying is if you have a function, and we'll call this negative 3, and we'll call the y value that goes with negative 3 negative 3. All right, so we have the first endpoint of my closed continuous interval is negative 3, negative 3. And over here, we'll call this 2, 0. So the endpoints that I'm looking at here, the closed interval would be from negative 3 to 2, which is spanning from here to here. Over that interval, I have a continuous function, so I've met all the criteria of the intermediate value theorem. The first endpoint y value is -3, and the second endpoint y value is 0. So all of the y values are, or the lower y value is -3, the upper y value is 0. What this function is saying is this. Consider the y value of, remember these were the y values that were generated, y value of the two endpoints. Think of a number between -3 and 0 like the number -1. Is there a value of x that generates a y value of -1? Well, clearly it has to be so, because to get from -3 to 0 on a continuous function, at some point we have to pass through -1. Now, the graph can go really high up and back down or whatever, but we have to pass through all of the y values from -3 to 0 to get, or on that continuous function. All right, let's look at an example. Let's use the intermediate value theorem to show that this cubic function, we know that a cubic function is continuous everywhere, that it has a 0 on the interval from 0 to 1. So we're trying to prove that this function has a 0. So the first thing I'm going to do is consider my endpoints. I know I have a closed interval. I know I have a continuous function. So I'm going to generate the y values at each endpoint. So I'm going to find f of 0. F of 0 is -1. I'm going to find the y value at the other endpoint. So f of 1 would be 1 plus 2 is 3. 3 minus 1 is 2. All right, so these are my y values of my endpoints, which I have a low of -1 and a high of 2. Well, if the function is continuous, then to get from -1 to 2, I clearly have to pass through 0 in order for that to happen. So since 0 is between 2 and -1, then there has to be a value of x that generates the y value of 0. So it's kind of a duh theorem. It makes common sense, but this is the formal definition of the intermediate value theorem. And you'll apply this in your homework tonight. Now the next thing I want to take a look at, and this was from problem number 63 in your homework, is this concept of forcing a piecewise function to be a continuous function. What you see here is we have a piecewise function, except one part that's truly missing. We don't have the coefficient of x squared in the second piece of the piecewise function. Now my job, according to the directions, is to find a such that f of x is continuous. All right, so let's talk about how to do that. Now, if you think about these two functions independently, x cubed is normally a continuous function when it's all by itself. Secondly, ax squared is some parabola, and parabolas are continuous when they're all by themselves. So we don't really have any discontinuities on the functions independently. So if there's going to be a problem, the problem would be occurring at x equal to 2, which is basically our break point between the two pieces of the functions. So what I'm going to do to determine this, obviously we could make a graph, but it's going to be kind of hard to graph ax squared when we don't know a. So I'm going to substitute 2 in place of x in the first piece. 2 cubed is 8, and if I were to graph this, because of the equal mark right here, that would be a closed circle on my graph. So when x is 2, y is 8. Now, I'm going to substitute 2 into the second piece. Even though it doesn't say equal to, I would want to know where to graph if there's going to be a hole, or I would want to know where to locate the graph or start the graph. So I'm going to substitute 2 in place of x. 2 squared is 4, and 4 times a is 4a. And that would be graphically an open circle because this time I don't have equal to. Well, keep in mind, I'm trying to force the function to be continuous. If the function is going to be continuous, then this value of x has to generate the same y value. Otherwise, I'm going to have a discontinuity. In other words, if we have the same x value and we want the function to be continuous, then we have to have the same y value. So the implication of that is that this y value of 8 has to equal to this y value of 4a. In order for that to happen, the value of a would be 2. And that's how you force or find a value that forces a function to be continuous.